In this video, we're going to work through an exam review on classifying differential equations and solving first-order differential equations. We're going to work through 10 exam-style problems, and we'll go over how to identify the type of each equation and then how to solve it step by step. To make it easier to follow along, be sure to download the free PDF of all these exam problems that I've linked down below in the description. Let's get started. Question 1 asks us to classify the given differential equation according to type, order, and linearity. This equation has ordinary derivatives, so it's classified as an ordinary differential equation. The highest order derivative in this equation is a second order derivative, so this equation is called a second order equation. Now let's think about linearity. Because all of the derivatives and y are raised to the first power, and all the coefficients are functions of x and not y, this equation is a linear differential equation. We would classify this equation as a second order linear ordinary differential equation. In question 2, we're asked to construct a slope field for the given differential equation and then use it to sketch an approximate solution curve that passes through the given point. The equation that we're given is dy dx is equal to y minus 1, and the initial point is y of 0 is equal to 2. To construct a slope field, you want to first create a table that contains x and y values and also the derivative dy dx. For this example, our table is only going to contain y and dy dx because the right-hand side of our equation, right here, is only a function of y. Let's choose 5 values for y, and I'm going to center these values around y is equal to 0. So I'm going to start with -2, and then we'll look at -1, 0, 1, and 2. To find what the derivative is equal to, we just go back up and look at the right-hand side. It's equal to y minus 1, so we're just going to subtract 1 from each value of y, and that gives us -3, -2, -1, 0, and 1. These values of dy dx are our slopes, and now we can go ahead and put them on our graph, and then we'll sketch the solution curve that passes through our point 0, 2. When y is equal to -2, our slope is equal to -3. Let's go ahead and label our graph. There's our y, there's our x. When y is -2, our slope is equal to -3. So we're going to draw lines that look like this. We'll just draw a couple of them. Now when y is -1, our slope is -2, so it's not quite as steep. And then when y is 0, our slope is -1. That one's easier to draw. Then we go up to y is equal to 1, and our slope is 0, so we're just going to have a horizontal line. And then our last one, when y is 2, our slope is 1. You can add more lines if you want, but I think this just gives us enough to be able to draw our solution curve. The solution curve that we want to draw is going to go through the point x is 0, y is 2, and that's this point right here. And our curve is going to look like this. It is going to start at our horizontal line, which is also the equilibrium solution. And it's going to come up, and it's going to look like this. This just gives us a basic idea of what the solution curve looks like. Let's now look at question 3. In this question, we are given an autonomous first-order differential equation, and we're asked to find 3 things. The first thing we want to find is the critical points and the equilibrium solution or solutions. An autonomous first-order differential equation will have critical points and equilibrium solutions where the derivative In this case, dy dt is equal to 0. So let's start, and let's take our right-hand side and set it equal to 0. This gives us y minus 1 is equal to 0, and y plus 2 is equal to 0. So we have y is equal to 1, and y is equal to minus 2. Those are called our equilibrium solutions. And then our critical points we'll label as C1 and C2. So we'll say C1 is equal to 1, and C2 is negative 2. They're just the numbers that y is equal to. The second thing we're asked to do is construct the one-dimensional phase portrait. Our phase portrait is going to look like this. It's a line of the values of y. And what you're going to do is on this line, you're going to put your equilibrium solutions. We have 2 of them. Y is equal to 1, and y is equal to minus 2. Now what we have to do is indicate on this line if the solution is increasing or decreasing. The way we're going to do that is we're going to calculate our derivative, dy dt, at the points in between our critical points. Remember that dy dt is just this function right here, y minus 1 squared times y plus 2. If we pick a point less than minus 2, say minus 3, this first term is positive, and then the second term is negative, so we're going to get a negative derivative. And that means our solution in this region is going to be decreasing. That just means the y values are getting smaller. If we pick a point between minus 2 and 0, we could say y is equal to 0. Then our derivative is going to be positive. Then our solutions are going to be increasing. And then lastly, if we look at our region on the right, our derivative is going to be positive, and our solutions again increase. Let's now take these arrows and put them over on our graph. For points above y is equal to 1, our solution is increasing, so we put an up arrow. Between negative 2 and 1, it's increasing. So we're going to put an up arrow here and here. You want to put an arrow beside each critical point. And then in the region less than minus 2, the solution is decreasing, so we have a down arrow. And that's the phase portrait. Now let's look at the last one. In part C, we are asked to classify each of our critical points, those are the points 1 and minus 2, as stable, unstable, or semi-stable. Let's look at the point y is equal to 1. Notice with this one that below 1, solutions are going toward this point, but above 1, solutions are going away from that point. That means that point is called semi-stable. So we would say for part C, y is equal to 1 is semi-stable. Now let's look at y is equal to minus 2. Notice for that one that solutions are moving away from that point. So we would say y is equal to minus 2 is unstable. And that's all there is for this problem. Let's go to the next one. In question 4, we're going to solve the differential equation dy dx is equal to x times 1 plus y. Notice that this equation can be written like this. We can say dy dx, which is equal to x times 1 plus y, can be written as a function of x times a function of y. This tells us that this is a separable differential equation. You always want to identify what type of equation you have first, and then you just have to go through the steps to solve it. The first thing that we want to do to solve this equation is we want to separate the variables. I'm going to go ahead and write all the steps over here so that you can remember them. When we separate variables, we're going to put all the variables that are the same on each side. So we're going to write this as dy all divided by 1 plus y is equal to x times dx. Our second step is to integrate both sides. So we're going to have the integral of 1 over 1 plus y times dy is equal to the integral of x dx. Now we can integrate. On the left-hand side, we get the natural log of the absolute value of 1 plus y. And on the right-hand side, we get x squared over 2. And then we can't forget to add on our constant, and I'm going to call that C1. For step 3, what we need to do is solve for y. Our y is inside the natural log, so what we're going to have to do is exponentiate both sides of the equation to get our y outside of the natural log. We'll write this as e to the natural log absolute 1 plus y is equal to e to the x squared over 2 plus c1. Now our left-hand side is just absolute 1 plus y, and then our right-hand side, we can split it up and write our constant term first. So we're going to write this as e to the c1 times e to the x squared divided by 2. Now let's get rid of the absolute value, and we're going to take that plus or minus from the absolute value and put it over here on the right. And we can combine it with our other constant. Now let's go ahead and solve for y. Y is plus or minus e to the c1 times e to the x squared divided by 2 minus 1. Now, the last thing that we want to do is rename our constant so our solution is a lot easier to work with. We're going to let c be equal to plus or minus e to the c1. So we can write our final answer as y is equal to c e to the x squared divided by 2 minus 1. And there's our solution. Let's now look at question 5. We're going to solve the initial value problem dy dx plus 2 times xy is equal to 2x, and our initial condition is y of 0 is equal to 1. Let's first determine what type of equation we're working with. Notice that this equation looks like this form. A1 of x times dy dx plus a0 of x times y is equal to g of x. This is a linear ordinary differential equation. Whenever you have a linear ordinary differential equation, you can always write it in standard form, and that standard form looks like this. Dy dx plus p of x times y is equal to q of x. The equation that we've been given is actually in this form, so we don't have to change it to that form. The first thing that we want to do when we're solving a linear ordinary differential equation is we want to find what's called the integrating factor. Let's go ahead and write down our equation first. We have dy dx plus 2xy is equal to 2x, and we'll hold off with the initial condition for now. To find the integrating factor, all you need to do is look at the term that multiplies y. Your integrating factor then, it's called mu of x, is equal to e to the integral of that term that I just highlighted in yellow, 2x dx. If we integrate this, this becomes e to the x squared, and that's our integrating factor. For step 2, all we have to do is multiply by our integrating factor, And then we're going to have to simplify. I'm writing these steps down because when I did reviews for my students, they found these really helpful. We're going to take e to the x squared and multiply it by every term in our equation. So we have e to the x squared times dy dx plus 2x e to the x squared times y, and that's equal to 2x e to the x squared. To simplify this, we're going to rewrite the left-hand side as the derivative with respect to x, e to the x squared times y. The left-hand side will always be the derivative of the integrating factor times y, and then our right-hand side stays the same. Since we are running out of room, I am going to take this expression and I'm going to bring it to the next page. Now we're ready for step 3. In step 3, we are going to integrate. We'll have the integral of the left, d dx, of e to the x squared times y dx. And then our right-hand side, we have the integral 2x e to the x squared times dx. Let's focus on the right-hand side for a minute. To integrate the right-hand side, we are going to have to use u substitution. I'm going to let u be equal to x squared because our du is 2x dx, and that's in our integral. So this becomes the integral of e to the u du, and that's just e to the u plus an arbitrary constant c. And then all we have to do is plug back in what u is equal to, so we get e to the x squared plus c. Now let's look at our left-hand side. On the left, we have an integral of a derivative, so that is just going to give us back what's inside, which is e to the x squared times y. And then our right-hand side we just found was e to the x squared plus c. In step 4, what we want to do is solve for y. To solve for y, all we're going to do is on each side of our equation, we're going to multiply by e to the minus x squared. You could also think about this as just dividing by e to the x squared. On the left, we get y, and then on the right, we get 1 plus c e to the minus x squared. We now have just one more step. Because we were given an initial value problem, we were told that y of 0 is equal to 1. What we have to do is we have to solve for c. In our equation right here, we are going to let x be equal to 0 and y be equal to 1. On the left, we have 1, and then we have 1 plus c times e to the 0. E to the 0 is just 1, so that tells us that c is equal to 0. Now we can write down our final solution, which is just y is equal to 1. And that's our answer. The answer that we got is called a constant solution. In question 6, we are going to solve another differential equation. This one's a little bit more complicated than the other two that we've done. This differential equation is 2xy minus 3x squared times dx plus x squared plus 2y times dy. And then we have 0 on our right-hand side. This equation is of the form m of xy times dx plus n of xy times dy is equal to 0. You might recognize that form. This is the form for an exact or homogeneous ordinary differential equation. Now we have to figure out which one it is. Let's talk about homogeneous first. If an equation is homogeneous, the constant terms, which I have highlighted in pink, have to be of the same degree. Let's look at this term right here. X squared is degree 2, but 2y is degree 1. So that tells us that this equation is not homogeneous. Let's check to see if it is exact. So I'm going to actually write this down as our first step. We're going to check if it's exact. To do that, we have to check if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. The way I remember this is that the m multiplies dx, so we take the partial of m with respect to y. It's the variable that it doesn't multiply. Let's go ahead and do that. The partial of m with respect to y is the partial derivative with respect to y of 2xy minus 3x squared, and that is equal to 2x. Let's do something similar for n. We have the partial derivative of n with respect to x. That's d dx of n, which is x squared plus 2y, and that is equal to 2x. These two terms are the same, so we know that our equation is an exact equation. Now let's walk through the steps on how to solve this. For our second step, we want to set the partial derivative of a function f with respect to x equal to m, and then the partial derivative of f with respect to y equal to n. Let's do that. The partial derivative of f with respect to x is equal to m, which in our problem is 2xy minus 3x squared. And then the partial derivative of f with respect to y is x squared plus 2y. We're going to put the partial of f with respect to y in our pocket, hold on to it for a minute, and we'll use that in a little bit. What we're going to do in step 3 is work with the partial derivative of f with respect to x, and we're going to integrate it. So let's write down, we're going to integrate partial derivative of f with respect to x. We have the integral of the partial derivative of f with respect to x times dx is equal to the integral of our right-hand side, 2xy minus 3x squared times dx. Our whole goal in this is to find f of xy. On the left, we just have f of xy, and then on the right, we're integrating with respect to x, so we have x squared y minus x cubed, and now we have to add on an arbitrary constant, and that constant is going to be a function of y instead of just c. In step 4, we are going to find the partial derivative of f with respect to y, and then we're going to set it equal to the term that we were holding on to. Looking back at step 3, the partial derivative of f with respect to y, I'm looking right here. Our partial derivative is going to be x squared plus g prime at y. And we're going to set that equal to this term right here that we've been holding on to. And that is x squared plus 2y. In step 5, we are going to solve for g of y. We're going to set this term equal to that term because our x squares can be subtracted off. We have g prime at y is equal to 2y. And then we'll integrate that, and that tells us that g of y is equal to y squared. And because it's just a function of y, we add on a constant, c1. In step 6, we are going to write the solution f of xy is equal to an arbitrary constant c. This form here is the solution to any exact equation. Let's look back up right here and write that down. Except now we can plug in what g of y is. We have f of xy is equal to x squared y minus x cubed plus our g of y, which we just found to be y squared plus c1. And we have to set that equal to a constant, and I'm going to set it to be c2 because then we're going to combine our constants. Let's let our constant c be c2 minus c1. So we're just going to pull this c1 over here. And then we can write our solution as x squared y minus x cubed plus y squared is equal to c. And that's the solution to this exact differential equation. Let's now look at question 7. We are going to solve the initial value problem, x squared plus y squared times dx minus xy times dy is equal to 0. And then we're given the condition that y of 1 is equal to 1. This equation looks really similar to the one that we just solved. It's of the form m of xy times dx plus n of xy times dy is equal to 0. This equation could be an exact or a homogeneous. Let's think about homogeneous first. X squared plus y squared, those terms are each of degree 2. Minus xy is also of degree 2. So let's write down coefficients are equal to degree 2. Doesn't matter the degree, it just matters that they're the same. And that tells us that this equation is a homogeneous differential equation. Just for completeness, let's check exact. If we take the partial of m with respect to y, that gives us 2y. And then if we take the partial of n with respect to x, we get minus y. And those two are not equal, so it is not an exact equation. Let's now go through the solution. Our first step is to make a change of variables. When you're deciding which change of variables to make, you want to look at both of the coefficients. We have x squared plus y squared, and then we have minus xy. And you want to choose the term that's more simple. Our first one has an x squared and a y squared, so it has two quantities. And then the second one just has an x times a y, so that's just one quantity. So we would say that this is the more simple term. This term multiplies dy. So we are going to make the change of variables that y is equal to u times x. Let's highlight that. Now our second step is to differentiate. We're going to differentiate y is equal to u times x. We have dy dx on the left. And then we have, using the product rule, u times the derivative of x, which is just 1, plus x times du dx. We then convert this to differential form, and we get dy is equal to u dx plus x du. You can always go directly to that if you're comfortable doing that. Let's go ahead and highlight that because we're going to need it. Our next step is to substitute y and dy into our equation. Let's write down our equation first. I think that'll make it easier. X squared plus y squared dx minus xy dy is equal to 0. We have x squared, and now y squared is u squared x squared times dx minus x times y, which is u times x. And then we have our dy, u dx plus x du. Now let's multiply this through. This gives us x squared dx plus u squared x squared dx minus x squared u squared dx minus x cubed u du. And we have a 0 on our right-hand side. And I just realized I didn't write 0 on the right-hand side for the line above it. Now let's see what cancels out. These two terms cancel, which is nice, and then nothing else cancels. Let's rewrite this and put the du on the right. So we have x squared dx is equal to x cubed u du. You may recognize now the form of this equation. This is a separable differential equation. So for step 4, we are going to solve the separable differential equation. Let's put all the x's on the left and the u's on the right. So we'll divide by x cubed, and we have 1 over x dx is equal to u times du. Now we can integrate both sides. On the left, we have natural log absolute value of x. And on the right, we have u squared over 2 plus an arbitrary constant that I'm going to call c. Whenever I have an initial condition, I always just call the constant c because we're just going to solve for it and we're not going to have to rename it later. Now what we want to do is put our u back in terms of y. So let's go back up here and look. We had y is equal to u times x. We'll write that down. Y is equal to u times x. So that tells us that u is equal to y divided by x. On the left, we have natural log absolute x. But now on the right, we can write this as 1/2 times y squared over x squared plus c. In step 5, what we want to do is solve for c and then y. Our initial condition, go back up, is y of 1 is equal to 1. So we're going to let x be 1 and y be 1. This gives us natural log absolute 1 is equal to 1/2 plus c. The natural log of 1 is equal to 0. So this is equal to 0, and c is equal to minus 1/2. Let's now put that back in. We have natural log absolute value x is equal to 1/2 times y squared over x squared minus 1/2. Let's multiply both sides of the equation by 2. So we have 2 natural log absolute x is equal to y squared over x squared minus 1. Let's bring our 1 to the right-hand side. So we have 2 natural log absolute x plus 1 is equal to y squared over x squared. And then we can solve for y squared. Y squared is going to be x squared times 2 natural log absolute x plus 1. And that gives us y is equal to plus or minus the square root of x squared times 2 natural log absolute x plus 1. We can bring the x squared out of the square root. We don't have to bring it out as an absolute value because we already have plus or minus. So this is just plus or minus x square root 2 natural log absolute x plus 1. Now, it feels like we're done, but we're not quite done. We have to be really careful with the plus or minus. We were told that y of 1 is equal to 1. So let's see if this holds. If we let y be equal to 1, we have 1 on the left, and then we're going to let x be equal to 1, and we have plus or minus 1 square root 2 natural log 1 plus 1. This is just equal to 1, so we get plus or minus 1. We can't have 1 is equal to plus or minus 1, so we want to only include the positive root. Our solution then is y is equal to x square root 2 natural log absolute x plus 1. And that's our final answer. Let's now go on to our next one. This is a long review, so if you need to take a break, now's probably a really good time to take a quick break and then come back. In question 8, we're asked to solve the differential equation dy dx plus 1 over x times y is equal to x times y squared. This equation looks similar to a first-order linear ODE, but it's a bit different because it has a y squared on the right-hand side. This equation is a Bernoulli differential equation. And we know that because it's of the form dy dx plus p of x times y is equal to f of x times y to the n. If it didn't have that y to the n, it would be a linear first-order ODE. The first thing that we're going to do to solve this equation is to find n. Our equation is dy dx plus 1 over x times y is equal to x times y squared. This tells us that n is equal to 2. I'm going to highlight that because we're going to need that in a minute. Our next step is to make the substitution that u is equal to y to the 1 minus n. So we have u is equal to y to the 1 minus n is equal to 2, so this is y to the 1 minus 2, which is y to the minus 1. So let's put over here that u is equal to y to the minus 1, and I'm going to highlight that because we're also going to need that. Step 3 prepares us for converting this equation that's now in terms of y to an equation in terms of u. So what we're going to do is we're going to find du dx, and then we'll find dy dx so that we can substitute that back into our equation. Looking at the formula that I highlighted over on the right in blue, we can find du dx, and that is minus y to the minus 2 times dy dx. We can then solve for dy dx. I'm going to go ahead and pull that over here to the left. And it is minus y squared times du dx. Let's highlight this because we are going to need that to substitute it back into our equation. Step 4 is where we are going to put what we just found, dy dx, into our equation, and we're going to simplify. Let's go ahead and rewrite our equation. We have dy dx plus 1 over x times y is equal to x times y squared. Our dy dx is now minus y squared du dx plus 1 over x times y is equal to xy squared. Let's now get du dx all by itself. So we're going to divide by minus y squared. This gives us minus 1 over x, and then y divided by y squared gives us a 1 over y. And then on the right, we just have minus x. What we need to do now is to put this equation all in terms of u. So what we're going to do is we're going to change y to u. Let's go back up here. Right up here, we had the formula that u is equal to y to the minus 1. Let me write that down right here. So we have u is y to the minus 1. And now we can write our equation as du dx minus 1 over x times u is equal to minus x. You may recognize the form of this equation. This is a linear first-order ordinary differential equation, and we know how to solve that. So let's write down for step 6, we are going to solve the linear ODE for u, and then for y. So we'll just make a change of variables. Once we have the equation for u, we'll put it back in terms of y. To solve this linear equation, we need to first find the integrating factor. The integrating factor is going to use the term that multiplies u. Our integrating factor is mu of x, and it is e to the integral minus 1 over x dx. This is e to the minus natural log x. We can then pull the negative that's in front of the log up into the power and write it as e to the natural log x to the minus 1. And this gives us an answer of x to the minus 1, or 1 over x. We didn't need to write an absolute value for x because we're going to take this integrating factor and multiply every term in our equation by that factor, and the plus minus would just cancel out. Let's go ahead and let's do that. We're going to multiply every term by 1 over x. This gives us a minus 1 over x squared times u. And on the right-hand side, we just have minus 1. Now let's simplify the left-hand side. It always ends up being the derivative of the integrating factor, which is our 1 over x times u. And then the right-hand side stays the same. Now we can integrate both sides of our equation. On the left, we just have the integral of a derivative, so we just get back 1 over x times u. And on the right-hand side, the integral of minus 1 is minus x plus c. We can then solve for u, and it is minus x squared plus cx. Hang with me, we are almost done. Now what we have to do is let u be equal to, let's go up here, and I'll put a red check here so you can see what I'm looking at. U is y to the minus 1. So we have 1 divided by y is equal to minus x squared plus cx. And then we can rewrite this better by taking the inverse of both sides of the equation. And this gives us that y is equal to 1 all divided by minus x squared plus cx, and we can rewrite this once more and pull out an x in the denominator. So we have 1 divided by x times c minus x, and that's the best way that we can write the solution. Question 9 is an application problem. I have a video on lots of application problems, and for this review, I chose this problem because it's probably one of the most common ones. This application problem uses Newton's law of cooling. We have a cup of coffee that is initially at 160 degrees Fahrenheit, and it's placed in a room where the ambient temperature is 70 degrees Fahrenheit. And then we're told one more piece of information. After 5 minutes, the coffee has cooled to 130 degrees Fahrenheit. We want to do two things. The first thing that we're going to do is set up and solve the differential equation for the temperature T. For this part, you need to know a little bit about Newton's law of cooling. Newton's law of cooling tells us that the rate of change of the temperature with respect to time is proportional to the difference between the temperature of the coffee and the temperature of the room, which is 70 degrees. We can then replace our proportionality with an equal sign and a constant and write this as dt is equal to minus k times t minus 70 degrees. We put the minus there because the temperature of the coffee is going to be decreasing because it starts at a higher temperature than the room temperature. We can now solve this. Notice that this is a separable differential equation. So we're going to put the temperature T variables on one side and the time on the other. We'll write this as d capital T all divided by T minus 70 degrees is equal to minus K times d little t. Now we can go ahead and integrate both sides. On the left, we have the natural log absolute value T minus 70 degrees. And on the right, we have a minus K little t plus C. To get the temperature T out of the natural log, we are going to exponentiate both sides. So on the left, we just end up with T minus 70 degrees. We don't need the absolute value because the temperature T is never going to be smaller than 70 degrees. And then on the right, we have e to the minus kt plus c. Let's pull the 70 to the right. So we get our temperature T is e to the minus kt plus c plus 70 degrees. Notice that we have two constants. We have k and we have c, and we can find out what those constants are by using the conditions that we were given. We were told that the temperature of the coffee at time 0 is 160 degrees. And then we were told after 5 minutes, so that's capital T of 5, the coffee is 130 degrees. And we can use these to find K and C. Let's start with T of 0. We have T at 0 is equal to e to the 0, which is 1. So this is just e to the c plus 70 degrees. And that is equal to 160 degrees. So we know that e to the c is equal to 90 degrees. We can plug this in. So we now have our temperature T is equal to 90 degrees. Let me make sure you understand why I did that. Let's go over here. If we have e to the a plus b, this is e to the a times e to the b. So in our case, this was e to the c times e to the minus kt. So we have 90 degrees times e to the minus kt plus 70 degrees. Now we need to find k. And we're going to use our other condition to do that. Let's let our time t be equal to 5. So we have t at 5 is equal to 90 degrees times e to the minus k times 5 plus 70 degrees, and that is 130 degrees. Let's subtract 70 degrees, and we have 90 degrees times e to the minus 5k is equal to 60 degrees. We'll divide by 90. We end up with e to the minus k times 5 is equal to 6 divided by 9, which is just 2/3. Let's take the natural log of both sides to get our k out of the exponent. So we have minus k times 5 is the natural log of 2/3, and that tells us that k is equal to minus natural log 2/3 all divided by 5, and we can absorb that negative into the natural log and just flip the fraction. So this becomes natural log 3/2 all divided by 5. Now let's look back to this equation right here, and let's plug in what our k value is. This gives us t is equal to 90 degrees times e to the minus natural log 3/2 times t over 5, I just grouped those two together, plus 70 degrees. We can rewrite this as 90 degrees times e to the natural log 3/2 times minus t over 5 plus 70 degrees. And then we're going to use the property of logs that e to the a times b can be written as e to the a raised to the b power. This is our a, and this is our b. This gives us that our temperature at time t is 90 degrees times 3/2 to the minus t divided by 5 plus 70 degrees. Let's highlight this because that is our answer for the temperature of our coffee. Now let's go back up and look at the second part. For part B, we want to find the temperature after 15 minutes. What we're going to do is just let our time t be 15. So this is much easier than what we had to do in part A. We have 3/2 to the minus 15 over 5 plus 70 degrees. This gives us 90 degrees times 3/2 to the minus 3 plus 70 degrees. Put that in your calculator, and we get an approximate answer of 96.67 degrees Fahrenheit. That's the temperature of our coffee after 15 minutes. Question 10 is our last question, and it is one on a numerical method. In this question, we are going to use Euler's method to approximate the solution of this initial value problem at x is equal to 1.5. And we're going to use a step size h is equal to 0.1. Euler's method is used to approximate first-order ordinary differential equations that look like this. On the left, you have a derivative, such as dy dx, and on the right, you have a function of x and y. Euler's method gives us a way to calculate the solution of this equation, which is y as a function of x. And the way this works is we start at the point that we're given. In this case, we're starting at x is equal to 1. And then we use our step size, which is h, and we add h to this. So we have 1 plus h, which is 1.1. And then we find out what the approximation for y is for this x value. So that means we actually need a formula for y, and the formula from Euler's method is y sub n plus 1 is equal to y sub n plus h times f of xn yn. I have a video that derives this formula if you're interested. Let's now write down what y sub n plus 1 is if our function f is equal to x plus y. That comes from the original problem that we've been given. So we have y sub n plus 1 is equal to y sub n plus h, which is 0.1. So let's put in 0.1 times x plus y, and this is now xn plus yn. Let's highlight this because that's the formula that we're going to work off of. And then let's also make a note that our original x point, x0, is equal to 1, and our original y point is equal to 1. That comes from the blue initial condition in our problem. Once you have the formula set up, what you now need to do is set up a table. My table is going to have n, and then I'm going to have xn, and then yn. We're starting with x0, so n is going to be 0. Let's make a line here. And then x0 is 1, and y0 is 1. Our next point is going to be our previous point plus h, which is 0.1, so this becomes 1.1. We need to, let's go back up to the top, we need to find our approximate solution at 1.5. So down here in our chart, we are going to have to find y value for 1.2, 1.3, 1.4, and 1.5. So n is 1, 2, 3, 4, 5. Now we can go ahead and start computing our y values. I'm going to add that y0 is 1, and now we're going to do y1. So y1, looking up at our formula, highlighted in yellow, is going to be y0 plus 0.1 times x0 plus y0. Let's see what that is. That's going to be 1 plus 0.1. 1 plus 1 is 2, so this gives us 1.2. Now let's find y2. y2 is going to be the previous y, which we found to be 1.2, plus 0.1 times x1, which is 1.1, plus y1, which is 1.2, and that is equal to 1.43. Let's do the same thing for y3. The more we do it, you'll see the pattern that's going to emerge. y3 is going to be y2, which is 1.43, plus 0.1, times our previous x and y values, which is 1.2 plus 1.43, and this gives us a value of 1.693. You continue this same process, and you end up with y4 is equal to 1.9923. It might be good practice for you to do this and see if you can get that number. And then y5 is equal to 2.33153. Let's highlight this number because this is the approximate solution of our differential equation at x is equal to 1.5. And that's it. You now have a structured review of how to classify and solve the most common types of first-order differential equations. You should now be prepared to recognize which method applies and work through similar problems with confidence. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.